Hey everyone, and welcome. Today we are diving into one of the most iconic charts in all of science. It might just look like a bunch of boxes with letters, but the periodic table, it's actually the ultimate map to, well, everything in the universe, from the air you're breathing right now to the most distant stars. So let's get into it and start decoding this thing.
So here's our roadmap for this explainer. We're going to start by cracking the table's hidden code. Then we'll look at the great divide between metals and nonmetals. After that, we'll meet a couple of extreme element families, check out those super versatile transition metals, and finally, see what happens when these elements actually react with each other.
Okay, first things first, learning to read the map. And I want to be super clear here. The layout of the periodic table isn't random at all. Nope, it's a carefully constructed code that tells us a whole story about each and every element.
And here it is in all its glory. Every single known element, all organized perfectly based on its atomic structure and its, chemical personality. Honestly, just think of it as the ultimate cheat sheet for understanding the building blocks of our entire universe.
So, that's the big question, right? How does this incredibly organized chart actually work? How do we read all the information that's packed so neatly into its structure?
Well, it really starts with two simple rules. The horizontal rows going across, those are called periods, and the vertical columns going down, we call those groups. And as you read the table, from left to right, top to bottom, the elements are all lined up by their atomic number, which is just the number of protons in an atom's core.
And this right here, this brings us to the real secret of the groups. You should think of each vertical column as a family. The elements inside it, they all share similar family traits or chemical properties. And the reason for that is surprisingly simple. They all have the exact same number of electrons in their outermost shell, and that outer shell is what dictates how they're going to interact with other elements.
Now, the table's organization, it goes even deeper. If you look closely, you'll see this thick zigzag line running diagonally across it. This line is super important. It creates the Great Divide, separating all the elements into two main categories, metals and nonmetals.
And let me tell you, their differences are night and day. Metals, which you'll find on the left side of that line, are what we all typically picture. They're shiny, they're great conductors, they're easy to shape. But chemically, their main goal in life is to lose electrons. Nonmetals, over on the right, are the total opposite. They're often dull, brittle, terrible conductors, and their whole chemical mission is to gain electrons.
All right, let's zoom in on two of the most famous and honestly most reactive families on the entire table to see these group properties in action.
So way over on the far left, in group 1, we have the alkali metals. And then way over on the far right, just before you hit the super unreactive noble gases, you have the halogens in group 7. Now these two families are at completely opposite ends of the table, and they behave in these really fascinating opposite ways.
This table really highlights their clashing personalities. So get this, as you travel down the alkali metal family in group 1, they become more reactive, and their melting points actually drop. But for the halogens over in group 7, the trend is perfectly flipped. As you go down that group, they become less reactive, and their melting points go up. How cool is that?
So, this begs the question, why? Why on earth do two families of elements show such perfectly mirrored opposite trends when it comes to how they react?
For group 1, it's all about losing that one, single, lonely outer electron. As you go down the group, the atoms get bigger and bigger, adding more shells. This means that outer electron is getting further and further away from the nucleus's positive pull, which makes it way easier to just give away. And the easier it is to lose that electron, the more reactive the metal is. Now, for group 7, the story is completely flipped. Their goal is to gain one electron to get a full outer shell. But as you go down the group and the atoms get bigger, the nucleus has a weaker pull on any electrons trying to join the party. It actually becomes harder to attract that needed electron, and so their reactivity decreases. It's a perfect contrast.
Okay, now let's turn our attention to that big block right in the middle of the table, the transition metals. If the alkali metals and halogens are the extreme, dramatic siblings, these guys are the talented, versatile, and often really colorful middle children of the elemental world.
So what makes them so special? Well, it comes down to three key things. First, they are fantastic catalysts. They speed up chemical reactions without getting used up themselves. They're the whole reason the catalytic converter in your car can clean up exhaust fumes. Second, they're chemically flexible. They can lose different numbers of electrons depending on the situation, which we call having variable oxidation states.
And third, this flexibility allows them to form this amazing array of beautiful, vividly colored compounds.
Right, this whole idea of variable oxidation states, it basically means an element like iron can show up to the party with a +2 charge or a +3 charge. It's almost like it can't decide what it wants to be, which is what gives it such incredible chemical flexibility.
Okay, so we've learned the rules of the map. We know the layout. Now for the final section. Let's put it all together and watch these elements go head-to-head in a real reactivity showdown.
We're going to look at something called a displacement reaction. And the rule here is actually pretty simple. A more reactive element can basically just kick a less reactive element out of its compound and take its place, just like you're seeing in this diagram.
And this is where we see that halogen reactivity trend play out perfectly in the real world. Remember, we said reactivity decreases as we go down the group. So chlorine, sitting at the top, is the strongest. It can kick out both bromine and iodine from their compounds, no problem. Bromine, in the middle, is strong enough to displace iodine, but it can't mess with chlorine. And poor iodine at the bottom of the pecking order, well, it can't displace anyone. It's just perfect proof that the table's predictions actually hold true.
So, you see, the periodic table is so much more than just a list. By understanding its structure, its groups, its periods, its trends, we can literally read the story of each element, and most importantly, we can predict how it's going to behave. It turns chemistry from just memorizing stuff into actual deduction.
And that brings us to one final thought. The periodic table organizes everything we know, but the map isn't finished. Scientists are still creating heavier, super unstable elements in labs. So it really makes you wonder, right? What undiscovered elements are still out there just waiting to be added to the very edges of our map of the universe?